sorry, where was the screen? Yeah. Okay. So first of all, I'd like to thank the organizers for giving me the opportunity to speak here. My talk is about heterotic bundles on toric Calabi Yau manifolds based on this paper with Yang Hui Ha, Max Kreuzer, and Andre Lucas. So I'll start with some rudiments of heterotic smooth Calabi Yau models, and I'll describe how we actually construct the vectua using some algebraic geometric toolkits, and I'll finish with result and outlook. So our goal is to search for the standard models coming from heterotic EA times EA theory, and actually to do so in a rather systematic and algorithmic manner. The four-dimensional low-energy theory is obtained from compactifying an internal six-dimensional manifold X. And in order to preserve n equals 1 supersymmetry, basically two ingredients are required. First of all, we need to choose the internal manifold X to be a Calabi Yau threefold, and we should also turn on some internal gauge field on a holomorphic and stable vector bundle, so that this set of PDEs should be obeyed by the background. We'd like to impose some more constraints on the geometry so that we can get closer to the standard model. Firstly, the structure group of our vector bundle reduces the low energy gauge group, and the natural choice would be SU3, 4, or 5, respectively giving rise to E6, SO10, and SU5 gut groups in the low energy. And we have in mind of further breaking them down to the standard model group by discrete Wilson lines. Secondly, for the anomaly cancellation, the difference between these two C2s should be cancelled by five branes or by effective curve classes, and therefore we require that this actually lies in the Moricon of the Calabi Yau X. As for the particle spectrum, the net number of generations is given by the index of the vector bundle V, and this is the last condition we want to impose on the model building so that we can have 3 generations. Here, we actually have to allow for some positive integer kappa, because at the end of the day, we will want to quotient the manifold X by some freely acting discrete symmetry group of some positive order kappa. Of course, the possible values of kappa should be also constrained by the geometry. Now, before starting any systematic scan or systematic model building, we should first decide which classes of Calabi Yaus and vector bundles we want to deal with. As for the Calabi Yau threefolds, a prototypical construction is the quintic hypersurface in P4, which actually has a natural generalization to the class of hypersurface Calabi Yau threefolds in toric varieties. This has actually been completely classified by Kreuzer and Skarke. And actually, we had, this morning we had a talk by Brad Nelson about using this database for actually Swiss cheese. In the next slide, I will briefly sketch the idea of this Kreuzer-Skarke list, well, emphasizing on its combinatorial nature. As for the vector bundles, we will construct monad vector bundles, which have actually been studied by many papers in the context of string model building. We believe that they form a large class of holomorphic vector bundles on a given projective variety. So basically, the vector we will be constructing are monad bundles on hypersurface toric Calabi Yau threefolds. So let me now move on to a bit of details about the two constructions. I'll start with the Calabi Yau side of the story. For this, we make an extensive use of toric geometry, which can be thought of as a combinatorial toolkit for a certain type of algebraic varieties called toric varieties. It is combinatorial in that the required data lives in some integer lattices. So we basically imagine two auxiliary lattices of rank small n dual to each other via the natural inner product. And here, this rank small n turns out to be equal to the complex dimension of the toric variety described by the toric data. So we define a fan as a collection of cones in this lattice set n, nicely adjoined with one another. Instead of giving a full description of how this works, let me just give an illustrative two-dimensional example. So this is an example of a fan in Z2. So there are three two-dimensional cones shaded here, and also three one-dimensional cones or edges as these thick half lines. So what we do is we associate a complex coordinate to each of these three edges, and it turns out that these three complex coordinates just become the three homogeneous coordinates of P2. So in other words, drawing this toric diagram is kind of equivalent to giving this identification rule for P2. So this is already nice combinatorial picture of P2. Actually, it's not the end of the story. So some of the fans are actually good enough to describe not only toric varieties, but also Calabi Yau hypersurfaces embedded therein. And this example actually turns out to be a good fan. So this figure on the right is exactly the previous fan. And because it's a good fan, it has a nice, well-defined dual diagram in the dual lattice, where in the end we can get some bounded polytope region. And it turns out that each of the lattice points inside this polytope represents a cubic monomial of the three homogeneous coordinates. And this is how this toric data knows about a cubic hypersurface in P2 or a Calabi Yau one-fold. A natural generalization of the previous example can go as follows. So Calabi Yau three-folds can be constructed by four-dimensional good fans. However, they are not always smooth, and one sometimes has to slightly modify the toric data to guarantee the smoothness of the varieties. But actually, this is also a combinatorial process and has indeed been encoded in a computer called Pulp. And yeah, so this can deal with this smoothing issues. And I should also mention that toric data can easily determine all the Calabi Yau topologies relevant to our model building. So yeah, these combinatorics can deal with basically everything for our model building. So how many of them? So this morning we saw from Brian's talk that there arise 500 million Calabi Yau three-folds from four-dimensional good fans. So this is way too many, and then we want to restrict to some smaller subclass of all these. And one natural subclass are those Calabi Yau three-folds embedded in smooth ambient toric varieties. So the ambient varieties don't need to be smooth, but this is one natural subclass we can think of, for which there are 100 Calabi Yau three-folds, roughly. And a systematic model building has indeed been undertaken for this subclass, but unfortunately, we haven't been able to obtain any simple enough models here. As for some other natural subclass, one can think of Calabi Yau three-folds with small number of Kähler moduli, so either 1, 2, or 3 Kähler moduli, for which there are about 350 Calabi Yau three-folds. And this will be the class of Calabi Yau three-fold we'll be considering here. Now let me quickly describe the bundle side of the story. So the basic idea is to make use of line bundles as the building blocks, which are labeled by some integer vector in ZH11. And a monad is now, roughly speaking, a quotient of two sums of line bundles. So more precisely, a monad bundle V is defined by a short exact sequence of this form, where BI's and CA's here are some integer vectors in ZH11. Also, you can think of V as a kernel of this bundle map F, which can be thought of as an RC by RB polynomial matrix whose A, I entries are of degree or multi-degree CA minus BI. And we impose this positivity condition for the degrees. Right. So we'd like to explore the bundle topology, of course, and first comes the Chern classes. And they can be easily read off from the, so all these can be easily read off from the short exactness of the defining sequence. And upon imposing the physics constraints I've just described, we arrive at these algebraic equations of B's and C's of degree 0, 1, 2, and 3. Finally, for the bundle cohomology, the short exact sequence leads to this long exact sequence at the level of cohomology. And once we impose this positivity condition on the line bundles, we have this vanishing theorem. And then in particular, we have H2 of V vanishing. And this implies that we don't get any anti-families in our models. So this is good. And furthermore, it seems that this positivity of the line bundles is related to the bundle stability, which can be quite difficult if you want to do it in a brute force manner. So we impose this positivity condition as a natural constraint for our model building. So here is the result. We have undertaken a systematic scan for semi-realistic models, where semi-realistic means 3 generations, anomaly freeness, and gut group nature. And we have constructed about 1.7 million heterotic bundles over 31 Calabi Yau threefolds. And here is the statistics of the bundle indices. So as you can see, for majority of them, the indices are pretty large compared to 3. And indeed, after you impose some necessary conditions for the group order kappa, we are only left with about 2,000 heterotic bundles on 2 Calabi Yau threefolds. And these will be the surviving models we have. So to conclude, we've seen that thanks to the combinatorial nature of toric geometry and monad construction, heterotic model building turned into a constrained integer system. And we have obtained about 2,000 candidate models for semi-realistic heterotic models. Of course, for the details of the models, we need to better understand the geometry. And we are currently trying to figure out some issues with some simpler manifolds. So that's it. Thank you.
There's only 2 Calabi Yaus which are left. What distinguishes those?
Sorry.
There's only 2 Calabi Yaus.
Yeah, that's right. Yeah.
Are they special in any case?
So both of them have H1 equals 3, and they were basically selected by these criteria I just mentioned. And all these 2,000 bundles are of SU5 structure group, and yeah.
How many families do you get for these?
How many
families?
Three generations. Yeah.
So the discrete symmetry you want out is coupled. Is it always a Z2 or?
No. Actually, for one of these Calabi Yaus, we require group order 4, and for the other we require group order 8.
Fine.
Yeah.
Well, I don't see any more questions, so we thank the speaker again.